This is section 4.1, page 3. And we're going to do this example. List the vertices and their degrees and whether the vertex is odd or even. So we're going to go ahead and let's make a chart here. We'll write the vertex down first. Then we'll put the degree. And then we'll state whether it's odd or even. Oops, even. Okay, let's go ahead and get started. So the first vertex is A. And what's its degree? Well, it's got two edges coming out of it. So its degree is 2. Is it odd or even? Well, 2 is an even number. So we're going to go ahead and write down even. Okay, the next vertex is B there. What is its degree? 1, 2 edges coming out. So again, even. Then we're going to do C. Okay, now out of C we have 1, 2, 3. Just look at what's coming out of it. 3. So that would be odd. Out of D we have, let's see, we have 1, 2, 3. So we're going to list all those things that come out. So 3, which is odd, even though the 1 goes in a circle. And then D, let's see, E is next. So E, 1, 2. So that's even. And finally, F, 1, 2. So it's even. Okay, before you do your classwork, let's read this definition. It says a graph can be traced if you can begin at some vertex and draw the entire graph without lifting your pencil and without going over any edge more than once. So what I'd like you to do is go to your classwork, do 6 and 12, and answer all those questions while pausing the video. Then come back and we'll talk about those. Okay, so when you were doing these problems, it asked you whether or not the graph was connected, if the vertices were odd or even, and can the graph be traced? So connected, yes, you can see that there's no piece here that's left out that you can't get to. The odd vertices, well, if we go through and label them, we see that there's 3 here, 1, 2, 3 there, 1, 2, 3 there, 1, 2, 3 there. I just find it easiest to write it next to them. So they're all odd. A, B, C, D are odd. There are no even. And can it be traced? Well, hopefully you tried. And, you know, like if you start here, you go around here and around here and around here and then here. And then you have a problem. Either you go here or you go here. You can't go both without repeating. So the answer would be no. What about this one here? Okay, well, if we start and we do what we started to do before, we start here and we go here and here and around here and here and here and here. Did I get them all? Okay, we're going to have to mark them down because obviously I can't remember what we did there. Let's see. I'm going to start this time with down here at D because I know something. So let's start at D and try this. So let's go here. We're going to call this 1. We're going to go here. We're going to go outside 2. And then we're going to go here 3. And then we'll go up here 4. And then here 5. And then here 6. And here 7. So the answer to whether or not going to be traced is yes, it can be traced. Is it connected? Yes, clearly if it can be traced, it's connected. Which ones are odd and which ones are even vertices? Well, when we add this one, 1, 2, 3, 4, here. Here, 1, 2, 3, 4, here. Here, this was 3 and this was 3. So 3, let's circle this is the degree we have. The other was for labeling the order I was going in while tracing it. Okay, so odd number of vertices for C and D, even number of vertices for A and B. So the question is, why can one be traced and not the other? So maybe you're starting to get a feel for why this one was traced. Take a look at its vertices and look at this one. This one could be traced, that one couldn't be traced. And notice the difference between the vertices. Okay, so we're still kind of asking that question and don't quite know the answer. So, Euler's theorem. I believe I said Gauss. I meant Euler is the one who came up with this. So Euler, a graph can be traced if it is connected and has 0 or 2 odd vertices. So that's the clue here. It can be traced if it's connected, but then it has to have 0 or 2 odd vertices, no more than that. So that was our problem in that one example. All of the vertices were odd, and there were 4 of them. Okay, so note, if a graph has 2 odd vertices, then the tracing must begin at one of these and end at the other. If all of the vertices are even, then the tracing must begin and end at the same vertex. Okay, so we're going to use Euler's theorem to decide whether the graph can be traced. If the graph cannot be traced, state which condition of the theorem fails. All right, so if we look at this one here, we know to be traced, what do we need? We need it to be connected. It is connected, and have 0 or 2 odd vertices. So before we start figuring it out, let's figure out how many vertices are odd. So this one is going to be 1, 2. So I'm going to just put it next to it. 2 here, and 2 here. 1, 2, 3 for C, and 1, 2, 3 for D. Okay, so that tells us that we do have 2 odd vertices. So where does it say we're supposed to start? We're supposed to begin at one of these. So how about if we begin here? Now we have to be careful. We don't want to go across that bridge until we've done everything on the side, on the other side. So let's go ahead and start this way. We're going to go like this, okay? And then we take the bridge to get to the other piece of the graph, okay? So can it be traced? The answer is yes, it can be traced. Okay, traced. Okay, maybe we can say yes, it can be traced, okay? And then if not, we have to state why. Well, it can be, so we're good. Okay, how about this one? Can it be traced? Well, right off the bat, it's not connected, so no. So no, cannot be traced. Graph is not connected. Okay, what about this last one here? Well, it's all connected, so we're good there. Let's figure out the vertices. Odd or even? 1, 2, 3 here. 1, 2, 3 here. 1, 2, 3 here. 1, 2, 3, 4, 5. Okay, they are all odd. So we would say no, cannot be traced since there are 4 odd vertices. Euler's theorem says there can only be 0 or 2 odd vertices and be traceable. Okay, so hopefully you recognize this problem. This was our Königsberg Bridge problem. So we started off with seeing the land masses, and then we saw this example, which was putting it in graph form. Well, that's the Königsberg Bridge problem. The fact that every single one of these vertices was odd meant that we weren't going to be able to trace it like they wanted to. Okay, it's your turn to pause the video. Try number 12 again, okay? And then turn the video back on. So we're going to do these problems, and this time they wanted you to use Euler's theorem. So hopefully you went through and listed all your vertices, and you could see here it's not going to work because we have 4 odd vertices, so it can't be traced. Here we see that we're okay. We have 2 odd vertices, so it can be traced. And this one here, it cannot be traced because it's not connected. Okay, so back to the definition then. Definition says a path in a graph is a series of consecutive edges in which no edge is repeated. The number of edges in a path is called its length. Okay, on the next page, we will look at some examples of this.